Let's start with a basic correlation. In a hospital, a patient has a severe fever, and a thermometer nearby shows a high reading. Standard statistics notes this relationship perfectly. But if you walk into the room with a lighter and manually heat up that thermometer, does the patient suddenly develop a fever? Of course not. Doing is fundamentally different from seeing. Standard probability only looks at data patterns, making it blind to direction. Judea Pearl created do calculus to solve this by formalizing structural modifications to our systems. When we force a variable to change via the do operator, we mathematically cut it off from its natural historical environment, destroying all incoming arrows to that node. This gives us an elegant superpower, predicting the exact results of real-world physical changes using nothing but non-invasive, passive observational datasets. To fundamentally grasp do calculus, we must look closely at the deep mathematical chasm that separates standard conditional probability from physical causal intervention. On the left, we have standard probability, written as P of y given x. This represents passive conditioning. It is the domain of pure observation, acting like a motionless camera recording data as it flows from nature. On the right, do calculus introduces the explicit do operator. This instructs us to alter reality by forcing variable x to a fixed value. It models a physical action that disrupts the natural system. Think of carrying an umbrella as variable x, and rain as variable y. If we observe people opening umbrellas, the probability of rain updates to a very high percentage. But if we step in and force everyone outside to open an umbrella on a clear day, the probability of rain stays exactly at its baseline. The action does not command the clouds. Standard probability manipulates data by slicing and filtering an immutable dataset. Do calculus constructs a fundamentally modified alternate universe. How do we calculate the effect of an intervention without running a physical experiment? Judea Pearl proved that we only need 3 algebraic rules. These rules allow us to rewrite equations, gradually stripping away the do operators until only standard observational probabilities remain. Rule 1 deals with inserting or deleting passive observations. If we are intervening on x, and observing an extra variable z gives us absolutely no new information about our outcome y, then z is entirely irrelevant. We can mathematically erase z from the conditioning set. Rule 2 is the critical core, exchanging an action for an observation. If all backdoor paths influencing z are blocked in the causal graph, then physically forcing z to change has the exact same statistical impact as simply watching z change naturally. This is how we map correlations directly to causes. Rule 3 governs the pure removal of useless actions. If there is no open causal path from our potential action z to our target metric y, then forcing z to happen changes absolutely nothing. We can safely eliminate the action from our math entirely. By sequentially applying these 3 structural transformations, we achieve our ultimate target. We take an impossible, unmeasurable intervention query, scramble it through the graph, and anchor it safely back down to a standard observational data equation containing no do operators at all. While the 3 fundamental rules of do calculus are mathematically complete, applying them raw can feel like proving calculus theorems from first principles every single time. To make this practical, Judea Pearl operationalized these rules into 2 legendary algorithmic recipes: the backdoor and front door criteria. The backdoor criterion is your primary shield against confounding. Imagine evaluating if a drug X cures a disease Y. If an unobserved variable U like genetic predisposition or socioeconomic wealth, influences both choice of treatment and the outcome. Information leaks backward through a backdoor path, distorting our data. If we can identify a measurable variable Z, such as patient clinical subtypes, that effectively intercept or block this backdoor pipeline, we can isolate the true causal effect. Conditioning on Z acts as a physical shield. When a set of variables Z satisfies this criteria, do calculus yields the classic backdoor adjustment formula. This reweights the data across subgroups of Z, mathematically shifting our perspective from observation to true intervention. But what happens if the backdoor path is completely unmeasurable or hidden? Meaning we have no way to block it? This is where Pearl's genius provides an alternate route, the front door criterion. Instead of looking backward, we look forward. If treatment X operates exclusively through a measurable isolated mediator M before touching outcome Y, like smoking producing tar in lungs before causing cancer, we can exploit this isolated mechanism as a bridge. By combining two back-to-back applications of the backdoor adjustment, first measuring the effect of X on M, and then the confounded effect of M on Y, the front door formula completely eliminates the hidden confounder bias without ever measuring it directly. It is the ultimate mathematical magic trick of causal inference. You might wonder, can we bypass complex diagrams and just look at the raw data? The answer is a definitive no. Data alone is completely blind to causation. Columns of numbers show strong mathematical associations, but they never explain why those correlations exist. Consider a study where eating a diet X associates with high weight loss Y. The numbers alone cannot distinguish between two entirely opposite realities. Is the diet directly causing the weight loss? Or is an unobserved genetic factor Z simultaneously driving both your appetite and your baseline metabolic weight loss? Both scenarios generate the exact same data pool, meaning standard statistical formulas will spit out identical numbers, without an explicit directed acyclic graph, or DAG, to establish the direction of physical mechanics. Our analysis remains mathematically trapped. The DAG acts as our architectural blueprint of the physical system. It tells us exactly where information flows and which dependencies exist. Remember, the core operations of do calculus require us to modify the graph. When we apply a do intervention on X, Rule 2 and Rule 3 command us to physically sever all incoming parent arrows to that variable. If you don't know where the arrows point, you don't know which connections to cut, rendering the equations completely powerless. Before you write a single line of estimation code, train a model, or deploy an adjustment recipe, do calculus forces you to answer an absolute mathematical gatekeeper question. Is your target causal query identifiable? Identifiability is the ultimate green light. It asks whether an interventional truth hidden inside the hypothetical experimental realm can be perfectly reconstructed using nothing but data collected from passive observational reality. Think of the causal graph as the architectural locking mechanism of this vault. Do calculus acts as the master key, systematically cross-examining paths. If a valid reduction exists, the key unlocks the mechanism, translating the experimental question into standard, non-interventional math. However, do calculus is not a magic wand that can conjure answers out of thin air. If your graph contains dense, irrecoverable structures, such as an unmeasured latent confounder U that directly shadows both your treatment and your outcome with no intermediate mediators or clean proxies, the system breaks. In this scenario, do calculus provides a definitive, provable, no. It systematically demonstrates that the key has snapped in the lock. It proves that no amount of massive big data, complex neural networks, or advanced standard statistics can ever extract the true causal effect safely. It saves data scientists from chasing statistical ghosts by drawing an absolute mathematical perimeter around what is fundamentally unknowable. Calculus is no longer confined to epidemiology or econometrics. It is rapidly becoming a foundational asset in natural language processing. Current state-of-the-art large language models are essentially massive statistical correlation engines. They memorize structures over massive web corpora and predict subsequent words based on matching passive historical trends. This reliance on passive data introduces a profound systemic vulnerability: automated bias propagation. If historical training texts associate high-status medical careers with specific gender markers, the model treats that demographic skew as a fundamental linguistic law, reflecting prejudice in its outputs. Instead of blindly retraining a multi-million-dollar neural network from scratch, researchers now map the internal activations of transformer architectures as complex causal graphs. Here, the semantic-based text context C influences both intermediate layer embeddings E and gender concept spaces G, creating a backdoor path that corrupts our final textual token predictions T. By employing the calculus of counterfactual actions directly on hidden representations, we can execute a targeted do intervention. We mathematically overwrite the gender node, forcing it into a neutral or symmetric distribution. Do calculus dictates that we instantly slice away the incoming correlation path. This surgical manipulation breaks the toxic association without destroying the network's general linguistic intelligence. The modified internal embeddings produce balanced outcomes. Through do calculus, we transition natural language processing away from simple superficial pattern matching and toward verified, robust structural accountability.